My name is Pradeep, and this is Luke. We are both production engineers at Facebook. We specifically work on the MySQL infrastructure. So we are here today to basically share about how we manage production MySQL deployment at Facebook, and we'll talk about different components of the MySQL deployment. So here's the rough agenda for the talk. I will be talking about some of the concepts here, and Luke will be talking about some of the concepts. So we are basically going to discuss about how a MySQL instance at Facebook enters production, how it goes through various phases, and how it actually leaves production fleet. We're going to talk about how we copy data around in Facebook fleet, how we migrate shards, how we do balancing based on different parameters, and how we basically test our code to basically iterate faster to manage MySQL at Facebook. So before we get started, I wanted to quickly go over some of the terms we use frequently in the presentation, and that would become easier for you guys to follow the presentation. So I wanted three main things, basically. What's an instance, what's a shard, and what's a replica set. So an instance is nothing but a MySQL process listening on a specific port, and it serves some part of traffic. So our host can have many instances depending on the underlying storage space available. We have a concept called shard. A shard is nothing but a simple MySQL database. The names can be arbitrary strings, or they could be some ID forms. And then we have something called as the replica set. This is what is frequently used. So replica set is nothing but a collection of one master and n replicas. These master and replicas are located in different data centers. And depending on the topology of the underlying use case, the number of replicas can vary. So this is a typical example of how, the www looks, facebook.com is served. So you have the front-end web servers, and then you have the service discovery component, and then you have all the way in the back end some sort of replica set. So the service discovery framework is the source of truth for figuring out where a particular data lives in. And this framework is generic at Facebook. It is used for a variety of other purposes as well to figure out where things are. So if you can imagine a service discovery to be some sort of a big hash table, and you could ask for it like, hey, I have this shard. What is the writable copy of this shard? So all the client APIs are going to do is reference this table and get you the answer and the connection for that particular MySQL instance. Same goes with read-only copies, and also if you have any locality preferences, you could also use that information in the API to basically look up this table and get the right connection. So one significant advantage of having a service discovery framework like this is we can do our maintenance operations in the backend almost invisible to the user. So for example, let's say you have an instance and it has some sort of kernel upgrade or some sort of maintenance operation. All we have to do is basically disable that instance in this discovery framework while we work on it. So all the connections will automatically fall back on the master copy. You have a master which dies because of hardware failure or some sort of disk issue or whatever the reason might be. We can also do live promotion when we detect this and make the replica. Make the replica to be the new master. And while this has happened asynchronously in the background, we can initiate copy jobs to build a new replica. And once they are ready and caught up with replication, you can basically populate the table back. So this is how roughly, like, instances, clients basically use APIs which follow this thing. And all of the maintenance operations and promotions are very invisible to the application or the user. Okay. So let's talk about all these concepts together. So for example, you have the shard, db.helloworld. A shard always belongs to a given replica set. So let's say it belongs to a replica set 1, 2, 3, 4, 5. A replica set, as I mentioned, is hosted by different MySQL instances, having one master and n replicas. So in this case, let's say the instance in Prineville, Oregon is the master on 3306. And then you have in FTW, Fort Worth, Texas, you have the 3306, which is a replica, and another one in Forest City, which is another replica. So this is what roughly, if you put all of the things which I talked about, this is what it looks like. Now, as I mentioned earlier, a single host can have many MySQL instances. So the same same host, host123.prn, can have another instance which is serving a completely different replica set. So we have db.foobar that's hosted by another replica set 6789, and that has instances co-located in that machine. So, so all application owners and clients care about are shards, and rest of the thing is abstracted away from them. Okay. Next up. So let's talk about life cycle of a MySQL instance at Facebook. So every instance at Facebook has a state. A state indicates what the instance is basically doing at that point in time. States can be production, spare allocated, spare deallocated, reimage, and drained. Each of these has specific meaning. So as the name indicates, production is basically that is active at that point of time, and it is serving some sort of traffic, read or write. A spare is another state where you have instances just lying in the pool and they are ready to be used for replacing an existing production instance. Spare allocated, deallocated, reimage, these are transitionary states where you're actually doing some sort of maintenance operation on the instance. And drained is another state where you want to do some sort of investigation, like why MySQL process is not behaving the right way, or you want to do some sort of temporary maintenance and you don't want to initiate a copy for an existing instance. Every instance has some sort of metadata. The metadata has host name, port, the specific RPM version, and state, what I talked about. All of this is materialized in a MySQL shard, and that shard is the source of truth for what that instance has and how does it look like, and that is used by our automation code to make decisions based on that shard. Okay. Right. So let's walk through a couple of use cases here. So this is roughly a state transition diagram, and each of these states has an asynchronous processor, which basically handles an instance in that state. So, okay, let's talk about a case where you have a production instance which is broken and you need to replace it. So what would essentially happen is our automation would detect that, hey, there is a production instance which is broken. It will call an API to find the right spare which matches the current production instance. So it will go to the shard, specify a bunch of columns, and it will match the available spare for that production instance. It will allocate that for copy by moving from spare to spare allocated and initiate a copy process. And once the copy is complete and it's caught up with the replication with all the latest events from master, you mark that instance as production, and you take the existing production instance and move it to spare deallocated. So another workflow could be, now the instance is in spare deallocated. We have a set of predefined checks where we determine, can this instance be fixed somehow automatically and put it back to spare, Or if something fails, we basically send it to reimage, where it is sent through an entire provisioning cycle, and it comes up with operating system reinstall and disk reformatted and things like that. So each of these states, as I mentioned, has a processor which is basically written in Python, and they keep continuously scanning the fleet to get instances in each of these states and perform actions on them based on different metadata for that particular instance. So yeah, that's about lifecycle of MySQL instance. And the next topic is how do we do copies. I will let Luke continue that.
Test. So yeah, next I will go through a couple of basic tools we have in Facebook regarding how do we do data migration in terms of moving data around, and then later on I will piece all those components together to explain how do we do balancing based on those key components that we have in Facebook. So first, let's talk about how do we build a new instance using the existing data set for different purpose. So first I will talk about the different scenarios where we actually want to build a new instance using the existing data set. So essentially, host can be broken, or the MySQL instance can be broken due to various reasons, like replication failure or hardware failure. So in that case, we want to spawn up a new data set in a different healthy host, or a new instance in a healthy state to replace the broken one using the service discovery that we just talked about. Sometimes we want to move the data around in order to perform maintenance on certain asset, like racks or hosts, or even a power supply circuit. And then also we do move data around just simply for balancing purpose, so that for each individual host, we can achieve the maximum utilization for all the resources that we have on the host. So we use a tool we call MPS, which stands for MySQL Pool Scanner, to manage all those data migrations on the instance level. So the tool itself will just simply go through the couple of stages that we'll cover in the later part to build up a new MySQL instance using the existing data set. So let's go through the stage one of the other. First, we do allocation. Essentially, its job is to find the best slot for holding the data we're moving. And then it would take multiple factors into account. For example, the disk usage and the CPU footprint from the existing workload. And also it will consider spreading across multiple failure domains in order to have better fault tolerance. So once we know where to copy the data into, we'll start to set up the environment to be ready for holding the data. It does a couple of sanity checks and bootstrapping process. For example, making sure the host is at least healthy and there's no known hardware failures on the destination. And then install the right RPM version according to the setups we have for this specific data set. And then generate the right my.cnf, and then make sure the empty instance itself is in a healthy state to move on to the further migration. So next is the actual physical data migration. So for this step, we have different mechanisms to move the data around. Can divide this into two major categories, physical copies and logical copies. So we normally do a online physical copies for setting up a new instance, simply because the speed. So now that the whole fleet is on Flash, so we don't actually have too many production traffic effect while running online physical copies when building up a new instance. So for InnoDB engine, we use extra backup to take a snapshot in an online fashion and move it onto the destination. So for MyRox engine, we use the similar tool, which is called MyRox Hot Backup, to move the data around across different hosts. So under some scenarios, the physical copy is not feasible for us. For example, like if you're upgrading the MySQL across major versions, like say if you want build a new instance, new ATO instance based on the existing 5.6 dataset, the physical copy doesn't support that. Or if you're migrating across different engines, like for example, you want to build a new MyRox instance based on the existing InnoDB instance. These are all not supported by the physical copy, so we have to do a logical copy to set up the base data set. So in that case, we have two different ways to set up the data set. One is to do a online MySQL dump, which is pretty common tool that being used in the MySQL world. Or we can restore from the most recent backup, which is also generated from the MySQL dump. But by restoring from backup, we save the cost of running a long snapshot from the existing online services. So once we have the snapshot being bootstrapped on the destination host, then we need to set up the replication properly to be able to replay all the events that happened during the previous couple of stages so that the new instance can keep up with the master and getting ready for the upcoming production traffic. So there's not too much magic happening here. Essentially, we'll start the replication using the bin log position that got recorded as a part of the previous step. So under some scenarios, we were not able to connect it directly onto the existing master for fetching bin log events, simply because the data migration step might take too long, and then the master might not have all the bin log events that will be needed for the catch-up. So in that case, we have an internal component which is called bin log server that will serve as a intermediate master, and then serve bin log events by reading from the bin log backup device. And by using bin log server, we'll be able to cover the gap where the current master wasn't able to serve. And then once we caught up to a point where the bin log GTID range can be covered by the existing master, we'll switch from bin log server onto the existing master and keep the replication from there. And then after setting up the replication properly, we will simply just pulling the current second behind master on the new instance to make sure its data set is close to a point where it's up to date and ready for production traffic. So next we'll go through a data validation step to make sure the new instance that we built doesn't contain any data drift or corruption throughout the process. Because you may know that any software is vulnerable to human error or hardware corruption. So we want to make sure the new data set is consistent with what we have in the production environment. So in this stage, we'll use a checksum-based mechanism to compare the result from the checksum sequence between the current master and the new instance to make sure the data is identical between those two instances before putting them into production environment. So after data validation, the new instance is now ready to serve production traffic. And as we just explained, we use service discovery system to put this new instance into an enable state so that the clients now will notice this new instance and start to bring traffic onto the new node. And then once that is done, we can pull the broken ones outside of production if necessary. So apart from moving instance around, we also have this tool called online shard migration that will be enable us to move database around across different instances, which is a different level of data migration. So the idea of moving database around instead of using moving instance around is normally we'll find the application or the business can grow out of control at some point where a single instance wasn't able to hold the data anymore on a physical host. So in that case, we'll have to break the instance into multiple pieces by moving the database around to control the size or the footprint of each instance. So that's where we will need this online shard migration. So the tool we use for online shard migration is called OLM, which stands for Online Logical Migration. So the key concept of this is prepare the data into a new destination in an online fashion, and then catch up the events that are missing during the migration and bring the new data set up to a point where it's close to the existing data set, and do a address switch or registration in the service discovery to repoint the clients onto the new data set to achieve the purpose of splitting an instance. So here's a diagram showing how the online logical migration will be performed. So on the left side, you can see a fairly large instance on the left side containing two databases. One is database 1, which is 100 gigabyte in size. The other is 300 gigabyte in size. Assuming the host can only hold 500 gigabyte. So we're close to a point where we're going to fill up the disk. So we want to move one shard away from the existing instance so that we can continue to serve the traffic. And on the right side, we have a relatively small instance, which is only 50 gigabyte in size. So here we want explain how we're going to move this database 1 onto the right side. So first, we'll create a empty database on the right side to be able to hold the data. And then we'll use logical snapshot, which is a similar concept as a MySQL dump, but essentially start a transaction and start to dump the data onto local disk using a CSV format. And then break into smaller chunks so that we can gradually load down to the destination side. So once those two steps are done, we have a stale copy of the data on the right side now, which is fairly close to the left side. But there's still quite a lot of changes that are missing during the whole preparation stage. So then we'll need to replay the changes by using bin logs and filtering only the database that we are migrating, and then replay onto the destination side. And then we'll keep this, keep doing this logic in a couple of rounds up to a point where the data set on the right side is milliseconds behind the old data set. And then we think now is a good time for the actual final switch. So now that the data set on the right side is fairly up to date, we'll do a update on the service discovery system to repoint database 1 onto the new replica set, which is the address of the data set that we have already prepared. So once the new address is registered, all the clients will start to noticing that the address the destination of the shard has been changed, and then they will start to talking to the new replica set. And then once we verify there is no client-side error and there is no orphan connections or leftover connections on the source side, source replica set, we'll just drop the database on the source side to finish the whole logical migrations. So here's the same example of the logical migration, but on a different perspective. So OLM is essentially just preparing the data set and then register the new address in the service discovery system to perform the logical migration. So on the left, we have the old replica set, and then during the data migration, we clone a whole replica set using the existing data. And then essentially at the end, we do a registration in the service discovery to finish the whole migration. So on top of that, we also have a logical migration processor to be able to manage this shard movement at scale. Because the tool I just talked about only covers one single movement or migration. But we have tons of these kind of requests every day to be able to balance the fleet. So this process is designed to handle large-scale migration to solve the conflicts and also being responsible for picking the best destination for the shard movement and kick off the actual move, doing proper retry, cleanup after the migration. So now that we've covered two fundamental pieces of our automation, we can utilize them to do a very interesting thing, which is so-called balancing, to be able to reduce the fleet size by moving different data set around to be able to push the host level utilization to its limit. So like I said, the concept of balancing is essentially to to find the right place for the workload, so that on each host will achieve the maximum resource utilization. So let me explain how that works using a simplified example here. So, for example, if we only have 4 different kinds of workload in Facebook, and then the only bottleneck is on disk space usage, we want to fit into the minimum number of hosts as less as possible. So essentially, on the left side, we have 4 different kinds of workload. In total, they are consuming 1 terabyte disk space. And then if all the hosts that are available to us are in 500 gigabyte, theoretically, we only need 2 hosts to be able to serve these 4 different kinds of workload. But let's take an example showing how pool stacking or pool balancing can result into wasting resources. So first, here comes the workload 1, which is 400 gigabyte. There's nowhere to go but to place the workload randomly. And then the Replica Set 2 comes in. No magic happen here. We put it into host 2. And then the critical step happens here when we place in the Replica Set 3. So here we have 3 different choices. Let's assume that we just randomly put it onto host 2, which have 200 gigabytes free slot. And then what will happen here when the 4th workload comes in? It has nowhere to go because the existing 2 hosts essentially couldn't hold such a big workload. And then we have to put it onto host 3. And then we end up wasting 1 additional host for serving this 1 terabyte global workload. So that's just a quick illustration to show that how important balances is in order to achieve the maximum host level resource utilization, to be able to cut down the number of hosts we will be need for a certain workload. So using the same example to show how to do proper stacking, essentially there's not too much magic there, but to make sure whenever you're trying to put a workload, always find the optimal slot for it based on all the balancing metrics you're using. So here, disk space is the only balancing metric that we're using. But in the practical world, we have different metrics we will take into consideration, like, for example, CPU footprint, the memory usage, and even fault tolerance, the failure domain balancing, and also like peak time and non-peak time workload changes. All these metrics coming together and fitting into this mode, we'll be able to find the best slot for each data migration. So coming back to the example that here, apparently the best option for us is to put Replica 3 into host 1, and then when the 4th workload comes in, we can put it down to host 2, and then achieve the goal that using minimum number of machines to serve certain workload. So apart from proper stacking, as I explained, we also have the ability to control the shape of a workload. So here we call it carved shape. So essentially, this new example is showing a slightly different scenario, but surfacing a different issues. So right here, we still have 1 terabyte workload in total from 4 different workloads. But now they comes in a slightly different shapes. One is 400 gigabyte, and the rest 3 are 200 gigabyte. Let's see how much trouble this new setups can bring it to us. So the placement for the first 2 workload don't play any difference. We just put it onto 2 existing hosts that we have. And then when the 3rd one comes in, because we want to push the utilization up to a certain limit, we'll put it onto host 2, which again leave us no choice for the workload 4, because the existing slot size won't be big enough to hold the 4th workload. So essentially, when your workload changes, it might cause some additional overhead to your decision making, so that you weren't able to make the optimal decisions for placing a workload. So what we do here is actually, like I explained, each workload is compromised of a multiple database on an instance. And if we have the ability to move database around, we actually have the control over the shape of a workload. So if we look deep into these workload there, they consist of multiple database on each instance. And then we have the ability to move database around to be able to bring the question back to its original form, which we already illustrate in the first example. So by moving one database away from Replica Set 4 and onto Replica Set 2, we're back to the same question we've already solved before originally. And then we now be able to stack all four workloads onto two hosts to achieve the same balancing goal. So like I've just explained, all these fundamental pieces of the automations enable us to do lots of things across the infrastructure. But on the other hand, they're being heavily developed, and then we want to move fast on these components. So this puts a high demand of a reliable testing infrastructure to allow us to move fast without breaking things. So next, I will hand over to Pradeep to explain how do we test those components.
Thanks, Luke. Yeah, so most of our automation is in Python, and this testing infrastructure is specific to MySQL-related tooling. So the idea of, as Luke mentioned, like we want developers to like really move fast on these, different softwares we have. And all of these components manage very critical pieces of our infrastructure. So if copies doesn't work well, we may have a backlog of broken instances in production. If we don't do balancing properly, we may be utilizing our hardware very poorly. So it is important that these automation tooling work and have like really high availability. We definitely have unit tests, but the problem with unit tests are you kind of mock out all the backend connections. So you're essentially just testing a single function or a single API call. You want to be able to put everything like production, but not technically production, and verify your correctness of your software. So that's why we kind of focused on building like an end-to-end infrastructure, which is fast and which can provide you signals at diff time. Like when you're making the change, you are able to like verify whether your change is going to work or not. So the goals are like, as I mentioned, like you should be, or you would be able to build and canary packages based on the change you're making. Basically, whatever RPMs or tooling you need to build for a specific piece of automation, you should be able to build all that of your single change. And that this is all at runtime. You should be able to provide proper signals at before you land your change or before you commit your change or ship your change. You should be, as I mentioned, you should have like a production-like setup, but in a very isolated environment where you can be comfortable to break things and see why something breaks and fix your change. And yeah, you want to be able to iterate quickly on your change with confidence. So these were like the main fundamental goals which we had in mind when we developed our test infrastructure. So I'm going to explain this with a diagram. So the fundamental backbone of this entire testing infrastructure is we leverage VMs, and VMs have snapshots. So that is the key piece here. And we also have a way to like schedule tests. So you have a diff. Diff is nothing but your change or single commit or a bunch of changes together, and you want to be able to test. So what happens is when you publish a change, so we have a service which would basically check, okay, this is changing copies. Let me build all the packages required for testing the copy process. So it'll kick off that. We have a thrift service, which is basically, you can think of it as, the one where you request test assets, which are MySQL test assets. In this, it is a replica set or an instance or a full host. The testing service will basically look up the metadata which it has and find the right test asset, the virtual test asset in this case, and basically allocate that to the test. All your packages are basically canaried on that test asset, and you do some sort of fault injection testing and everything, and collect all the results and get that result at diff time. Now, what happens after the test? We basically, as I mentioned, use virtual machines. So we have virtual replica sets and virtual instances. Each virtual test asset has an active snapshot and a passive snapshot. So this allows us to quickly, go back to the original working state of the replica set after the test. It is, of course, assume that when you're developing something, nothing works the first time, so you do multiple iterations until you get it working. So you don't want to be, breaking the test asset. So the goal is to like how quickly you can have your, test pool back to normal. So that's why we chose to use VMs for this. So we have an idea of like what is the working copy of the like the virtual asset and the passive copy. And that's what is illustrated on the right-hand side. So when we deallocate, we basically switch the pointer around and reboot the VMs with the passive snapshot, and all the metadata is upgraded. It also has interfaces for developers to reserve test assets individually, like if you want to play around and test specific components under different failure scenarios. So you can like, hey, reserve me this asset for like 12 hours or 24 hours, and I want to play around with it. So all of this test assets have all the prod packages, all the prod-like setup, but it is isolated, so you're not breaking production, but you're just like playing around there and basically testing your changes very well. So we have caught a lot of bugs with this, so it has been a very good framework for all our MySQL infra team, and it has helped us with bugs where promotions would have broken if that change would have made it to production, because they were able to get the signal at diff time. They were able to identify, okay, this is the problem and this is how you fix it. Yep, that's about our testing infrastructure in a nutshell. And yep, that's all we had for today. So feel free to ask us any questions. The question is, storage attached to the local machine, is it like native flash or is it some sort of network device? So we use native flash on the host. We don't have any network devices for serving messages. Yes. Someone there? No? Yeah. Yes. So the question is, how granular the services have to be to test in? Yeah, okay, cool. So if you think of like the copy service, like we have, which is basically be able to replace an instance. So you can test up to that level. So you could like you could reserve a replica set and you can break an instance and you can do assertion that will the automation schedule a replacement, and will the replacement complete, and will the replacement be replicating properly. So all these assertions can be performed with this testing framework. Even shard migrations or even individual cases where you do a kill-9 on the master, and your expectation is that when that happens, your automation should detect that the master is down and perform like a quick promotion, and you can do all these sort of assertions as well with the testing infrastructure. Does that answer your question? Okay, cool. Okay. So the question is, what is the use of what is MySQL used for at Facebook? It is the backend for Facebook social graph. So whatever you see on Facebook graph is materialized in MySQL. It is also used as a backend for a variety of internal services, like, you can think of it like we have an internal MySQL cloud where people reserve MySQL for holding config data and any metadata about their service and things like that. So Messenger also, right? Yeah. Yeah, Messenger, your messages are like, you can search messages because your messages are somewhere materialized in MySQL. So we have blog posts about these things on code.facebook.com if you're like interested in how this is used. Cool, thanks. Yes? The question is, what is the most used storage engine? Do we know? Yeah, I will let Luke answer that.
So yeah, as Pradeep mentioned, the two major use case of MySQL deployment is the user data and the messengers, and then both two those use cases are using MyRocks. Yeah, RocksDB essentially. So RocksDB itself is just a storage engine, and we use the plugin API in MySQL to plug the RocksDB into a MySQL server so that users can use SQL to talk to the database, and the underlying physical storage format will be RocksDB.
The question is essentially, how do we manage different instances and states, and is it an automated system, or how do we manage that? So that was the question. So all of the things we talked about is all automated. There is code for everything. And we get notified or chirped or paged if something is not working. For example, if we see copies not succeeding in a certain duration of time, we have detections based on that. All the code for this is in Python, and it's basically automation here. Yep.
So when you move from the service directly in discovery from one master to another master, do you use like a router or something like that, or proxy, or how do you handle that?
So there will be no subscription mechanism to talk to the client. Essentially, the client is on their self to figure out the new address, but we will add some hint on the old the source replica set to hint the client to be reconnect onto the new resources. So essentially, once the final flip is done, we will mark the old database as unusable, and then the client connecting to the old database will start to receiving error. And as a part of the error, they will get a hint to connect to the new instance. Yeah.
So there's no proxy involved, and it's effectively infrastructure which indicates to the client that the master is somewhere else, and it will then basically use that to reach it.
Correct.
You'll never get any rights to an old master.
Correct. Yeah.
Do you ever get shards that are too big, so you need to split even the single shard?
Yes, definitely. So we hit that really often, which also inspires us to develop a new tool to be able to shard the existing data set automatically, so that the user have to do zero changes on the application side, and then the backend storage can be automatically split into multiple shards. But that's still being under developer at the moment. Yeah. So the user have to define the sharding key themselves, and that's the only thing they need to do. And once they've done that, we use similar logic as we've been using for logical migration. Essentially, instead of dump the whole data set, you dump the subset of the data set and then prepare onto different replica sets.
Just a follow-up on what you just said, like the hinting process for the client. Will you have any requests that fail because of that? And if so, how do you handle that?
For example, for the shard migration, the old database will be turned into a read-only mode, and then if you try to perform any DML on top of that, you will receive an error, yes. And then it's up to the client to decide what to do once you get this error and how to use the hint. But normally our recommendation is to retry and using the hint from the error message to reconnect to the right properties. One more question. Sorry, could you repeat that?
So regarding a database on an individual server instance, do you still try capacity planning to say next year's worth of growth, or do you end up just accepting migration?
So the question is, how do we do capacity management for each individual workload, right? So we don't do precise capacity management for individual workload because the diversity of our internal data set is so big that we can actually do it globally. Yeah, and it relies on balancing to reduce the footprint size. So the question is, what's the approximate global storage size, essentially,
Per host.
per host?
We have different.
Yeah, no matter it's global or per host, we're not allowed to talk about the actual number, unfortunately. Yeah. No, not approved. Sorry about that. But you know that we use direct attached flash, so you kind of get the rough number.
But these days you can get quite a lot of flash in the server if you really want to.
Yeah, right.
You can get a lot more than that in the server.
Right. Yeah. Yeah. All right. I guess we're. So we have different storage or stateful service solutions within Facebook. Yeah.
MySQL is one of them.
From the host capacity issue, basically is CPU the real thing? Because obviously with flash, and if you really have, it's quite hard to really utilize, even if you've got lots of instances running at things, or do you actually hit the capacity of the flash storage as well?
So the question is, what is the bottleneck on a host? So due to the high diversity of a workload, we actually didn't run into any bottleneck. So we were fortunate enough to piece all different kinds of workload together to push the utilization. Yeah. So essentially, the number of disk-heavy workload is pretty much the same amount compared to CPU-intensive workload. And also, now that we're moving to Marox, which gives us more flexibility into trading CPUs for disk space. So we have the knob to actually turn the shape of the workload by migrating to Marox.
So that helps a lot with the resource utilization, that you can reduce that a lot by moving things around to make use maximum use of hardware.
Correct, yeah.
Do you use that for choosing between Myrox and InnoDB as well, or
Can you repeat that?
do you use those characteristics between InnoDB and Myrox as well to balance the load, or it's just because you're moving towards Myrox?
It's a very good point, but we haven't looked into that deep yet.
Because Myrox does use more CPU than InnoDB, doesn't it?
Yes, if you use more aggressive compressions, yeah. The question is, do we see a regression in read performance by migrating to Marox? So I would say no, because the use case we migrated into Marox is actually suitable for Marox. So we won't move any like point, those heavy point queries workloads onto Marox because they fits to be better.
So query profile, you take that into account in which engine you're using as backend storage for the stuff.
Yes. So at the moment, it's still on a DBA's decision to make that whether this workload should fit into InnoDB or Marox. Okay, cool. Thank you, everyone.
Thanks.